Hey Rainy, good evening. Let's wait for others for 2 more minutes, then we can start the session. Okay, let's start the session. We were talking about the probability theory in our last class, and I want to continue from that only. So I'll give you a brief what we have discussed right so far in the probability theory. Okay, let me start. Yes, we have very few people today, but it's okay. Let's continue. Hey, Rohini, if you have any doubt, you can stop me anywhere. I'll be glad to solve your doubts. Okay. So let's start with the brief. So we in the last class we talked about probability, right? Where the values lies. Like what kind of values a probability can have. So it can have any continuous value between 0 and 1, right? And we all are aware about the continuous values, right? It could be, I mean, there are infinite possibilities between two numbers if we're talking about the continuous variables or values, right? So in between 0 and 1, we have infinite values. So the minimum a probability can have is 0, and the maximum probability can have is 1. I forgot to ask, is my voice clear? Are you able to hear me? Good. Okay. Yeah, we talked about some real life examples as well, like flipping a fair coin, rolling a fair six-sided die, right? Weather forecast. We try to find out their probabilities as well, right? So as you remember, the probability of heights we calculated using the sample space, right? Let's move to the next slide. So in general, the formula that we have discussed was the probability of something or an event will be the number of favorable outcomes divided by the total number of possible outcomes, right? And we discuss about the favorable outcomes and the possible outcomes as well, right? So we talked about experiment, sample space, right? An experiment is something that is happening, right? That process or action, basically the outcome. right? The sample space, the set of possible outcomes, right? The possibilities out of the total number of outcomes, right? Like let's say if I'm saying I'm throwing a die, so the total number of possible outcomes will be 1 to 6 anywhere, right? And but let's say the experiment that I'm performing, I want to have an even number. So the sample space of that will be 2, 4, and 6 only, because only three numbers belongs to even category, right? So that's how we decide the sample space. So it's nothing but the set of possible outcomes. Okay. Then we talked about event, right? So event is nothing but the subset of sample space, right, containing one or more possible outcomes. Right? The same thing that we have discussed, right? Probability of event we have already discussed, right? It's defined by the ratio. It is basically the ratio of number of favorable outcomes and the total number of outcomes. Okay. Uh, Key probability terminology we have already discussed: experiment, sample space, event, and probability of an event. Okay. We solved these example as well, like rolling a die and getting a three. Right. If you have any doubt, anyone here, I can repeat those examples. Right. You can let me know. You can text in the chat, right? If you want me to repeat it or not. Okay, great, Rohini. Let's go ahead. Relative frequency we discussed, right? It's the again the ratio of number of times the event occurs and the total number of trials that we do. Right? The best example was like I have a fair coin and I'm tossing it 100 times and I get 48 times had, right, out of those 100 trials, right? So the relative frequency in this case will be 48, the number of times event occurs, the head occurs, divided by the total number of experiments of the trials I have done. So in this case, it was 100. Okay. So that's why we got 0.48 probability in this case. Any doubts so far? Cool. So now, okay, cool. Thank you, Raini. So we talked about different probability events, right? And I assume like you were having some doubt in the last session about all these things, right? So I would like to repeat this, but not in detail. If you have any doubt, you can stop me, right? So I like try to finish them quickly only. So we talked about the independent events, right? So what are the independent events? Any of you wanna, tell me about this? Okay, you watched the recording. Now it's clear. Okay, but in the last class, there were a few more students. They had some doubt, right? So I want to quickly repeat it, right? It'll be great, Rohini, if you understood. You can, help me as well here, right? So that I'll be confident that you guys are aware about all these things, right? But I'll try to quickly, repeat it. So two events are independent if the occurrence of one is not affecting another. Okay. So let's say if I'm flipping a coin and rolling a die, so both are independent events, right? But now let's say I want to know the probability of getting a heads and a six on a die. What will be the probability, right? Now these two are independent, but these two things are happening together, right? So probability of getting these two things, how can we calculate, right? So the formula was, so it's an AND operation, right? A intersection B, right? Because I want these two things to happen together, right? So the formula for that is, so we represent it using the intersection operator P A intersection B. Okay. So in the case of independent events, the formula is P A, the event A, multiplied by probability of event B. Okay. We quickly see this example. We let's say probability of getting a heads from a pair coin will be 1 by 2, and probability of getting a 6 out of a 6 faced fair die will be 1 by 6, right? Now the probability of getting these two together, right, when I want to have like I want to have I want these two happens events to happen together, right? So the probability will be of this possibility will be the multiplication of both, as we discussed, right? So it'll be 1 by 2 into 1 by 6 is equal to 1 by 12. Okay. Now let's move to the dependent events. So two events are dependent if the occurrence of one event affects the probability of other. Okay. So you understood, right? What is a dependent event? If the probability of, or if the occurrence of one event affects the probability of another. Okay. Yeah. So you can take the example of drawing two cards without replacement from the deck, right? So Yeah. So the probability of getting an ace is 4 by 52, right? Because right now we have four aces. But let's say we want to draw a king now. But now, because of the last event that has happened in the past, right? So the number of cards has reduced by one, right? So the next probability will be 4 by 51. Yeah. So for others that have joined just now, so I was quickly recapping everything that we have discussed in the last class, right? If you have any doubt, you can stop me anytime, right? Or you can text in the chat, right? I'll clear all your doubts. Okay. So how to calculate the probability of the dependent events? Again, the same thing, right? I want these to have events to happen here, right? Okay. So the probability of these two events happening together will be P of A, the probability of event A into the probability of event B. Okay. So, but this formula is applicable only for the dependent events. Okay. Yeah. So, can anyone tell me now we have enough crowd, right? Can anyone tell me what are the mutually exclusive events? Anyone would like to take any guess? Okay. Yeah, cool. Okay, so I'll tell you if you don't want to take a guess, right? So two events are mutually exclusive if they cannot happen at the same time, right? So rolling a die, you cannot get both 3 and 5 at the same time because it's a one piece, right? So you will roll 3 first and then 5 first, right? So what is the probability of getting these two together, right? So it is like P A intersection. So A union B, we represent this mutually exclusive events as P A union B. So the probability of getting A and B, right, together as in one after another, right? Because I'm doing this event simultaneously, right? So just after three, getting a five, right? What will be the probability of that? It'll be P of A plus P of B. So getting the probability 3 out of a die is 1 by 6 again, and for the probability of getting the probability getting 5 out of a die will be 1 by 6 again, right? So what will be the probability of getting these two together in a simultaneous trial, right? And as we know, these events are mutually exclusive, right? Because they cannot happen at the same time. So in this case, we will not be multiplying it, right? We'll be summing them up, PA plus PB. So the probability for event A for number 3 was 1 by 6. Similarly, for 5 was 1 by 6. The final answer is 2 by 6, that is 1 by 3. Any doubt so far? Anyone? Okay, cool. So let's move to the next part, that was the complementary event. This was the simplest one, right? The complement of Okay, Justin, thank you. So the complement of event is a probability that A does not happen, right? It just is nothing but the because you know the max probability, right, is one. So if you want to know about like let's say the event is six and I want to know about the probability of not rolling a six, right? So out of six, like there are five other events as well on a die, right? So we can directly calculate that as well. That'll be 5 by 6 because we know the sample space, right? Where six is not coming. But if you directly want to calculate that, so let's say you don't know how many total possible outcomes are there, right? In that scenario, you can subtract it by one, subtract it from one. Okay. So let's say if I'm saying the probability of happening something is 1 by 23, right? So what will be the probability of not this happening, right? So you can just basically subtract it from 1 minus 1 by 23. Okay. Cool. Let's move to the next thing. That was the addition rule that we have discussed, right? Okay, so here, if we want so it's an OR event, right? As we have discussed. So we want to know what is the probability of getting a or drawing a rad card or an ace from a deck. Okay, so formula for this is PA plus PB minus PA intersection B. Okay, but as we discussed, right? If A and B are mutually exclusive event, the probability of having A and B together will be zero, right? Because these two events cannot happen simultaneously, right? So this will happen sequentially. Okay. So in this case, for mutually exclusive category, for mutually exclusive event, your formula will be addition rule formula will be P plus PB. But if it is a dependent event, like this example, because here we are talking about cards, because if you draw one card, next will depend on that only. Okay, so here, yeah, so the probability of just getting a red card will be 26 out of 52, because we know there are 26 red cards in the deck, right? And similarly, what will the probability of getting an ace will be 4 out of 52. This is just the probability of that particular event, right? Here we are not saying that this is happening one after another simultaneously, right? Okay, and probability of happening, like probability of getting these two things together, right? So you remember from the last category, right? So this is the dependent one. Okay, so probability of getting a rad ace, right? So what will be the probability of getting that? So we have only two rad aces, right? Either it will be heart or diamonds, right? So the probability of that will be 2 by 52. Okay, now we'll put all those values in the formula. So the PA is PA, we know P if P of red, probability of getting a red card, that is nothing but 26 by 52, plus probability of getting an ace, that is nothing but 4 divided by 52, subtracting the probability of getting a red ace. Okay, that is 2 by 52. So that final answer will be 0.538. Any doubt so far? Okay, I'm guessing it's no. Okay. So the last rule, and I mean the one more rule that we have discussed was the multiplication rule, right? So it's for and events. And events means both are happening together. Okay. So this is for independent events, right? The formula. Okay. So in this case, PA and B are happening together will be PA cross PB. Okay. So again, it's an activity for you. We have already discussed, find the probability of rolling two sixes in a row, right? What will it be? Can anyone guess? If you know the answer, please write it in chat. Meanwhile, I'm moving to the next important section that we were discussing in our last class, and I guess everyone have some doubts about it, right? I would like to know how many of you have doubt in the conditional probability. Go ahead, guys. Yes, no, you can write it in chat. Otherwise, I'll skip it. Cool. Okay, I guess I'm considering first time I'm considering it as no, because I know you all of you have some doubts when we were discussing with the conditional probability, right? So let's talk about it in detail today again. Okay. So what is the conditional probability, right? So conditional probability is the probability of an event, right? You guys know what is an event, right? Probability of an event occurring given that another event has already occurred. Okay, you're getting the point. So the difference here is, right, it's not like the things that we have discussed, right? Independent in case of independent events, things are happening together, right? So we talk like we discussed about calculating the probability of happening, getting a die, getting a six from a die and a heads from a coin, right? Here I'm saying, let's say if I'm talking about those two events only, I'm saying I've already got a head from the coin. That event has already occurred. Now what is the probability of getting a six from the die? Okay, good with the example. Okay, so it basically helps us in refining our predictions based on the additional information, right? Because we know some event has already occurred, right? So you will not realize like how can we use it in real world cases. I'll tell you, some of the real world example as well, right? Okay, let's discuss about the formula first. Okay, so the formula for this, right? P of A given B has already occurred. Okay, will be P A and B, probability of having A and B together divided by the probability of B. Okay, so doubt, any doubt? Are we good with the terminology? Okay, I'm considering this again. Yes, yes. Okay. So when to use the conditional probability? Okay. So first case is when events are dependent, right? So you guys are aware, right? What are the dependent events? I would Like anyone to unmute or like unmute and tell me about that? Vinay, Ashish, Rini, Justin, anyone would like to tell me what are the dependent events? We just discussed in our last class as well. Okay, I'm assuming all of you are aware about the dependent events. Okay, yeah. So let's take few examples, right? You know, so let's say you are drawing two cards from a deck, right? So in that case, right, the event, okay, yeah. So the event of happening, I mean, the probability of getting a second card will be dependent on the first card, right? What was that first card, right? So let's say I'm seeing what is the probability of getting an ace when an red ace has already uh, retrieved from the card deck of the cards, right? In the first attempt. Okay. So in that case, number of aces will be impacted, and even the total number of possible outcomes will be impacted, right? So you understood, right? And here we are using the concepts of the dependent events, right? Because these things are dependent. Okay. I'm assuming you guys understood. Let's move to the next part. Okay. So let's try to solve an example as well, right? So suppose you randomly draw two cards. It's like the similar example we just took, right? Suppose you randomly draw two cards from a deck of 52 cards. What is the probability that the second card is an ace? Okay. Given that first card drawn was an ace. Okay. So event A. So let's first of all, if you're when you're trying to solve the conditional probability, you have to identify the events in the question, right? Or events in the problem statement that you're trying to solve. Okay. So what are those events here? So first event is sorry, I the slide. Yeah. So what is the first event here? First event is drawing an ace on the first draw. Okay. And the second event is event B is drawing an ace on the second draw. Okay. Now, we have not mentioned, right, that drawing an ace on the second draw when in the first draw, an ace has already retrieved, right? But it's a information that they are giving you. That's why it's a conditional probability. Here we are not saying that these two events are happening together. Okay. So what will be the probability of getting an ace, right, from the first draw? Now we have in this case we have total number of four aces, right? Those are our favorable outcomes, and total number of possible outcomes are 52. Okay. Now, what is PB by A, right? Probability of getting event B, that is nothing but A is on the second draw, right? Given A has already occurred, right? Here we are calculating the dependent, probability dependent, right? So PB by A, again, same thing will be 3 divided by 51 because now we are left with the three aces only, and total number of possible outcomes are 51. Okay. Applying the conditional formula. Okay. So PB by A again is this is the one. Okay. So first we will calculate P A intersection B, P of A into PB by A. We'll just impute all those values that we have calculated. Okay. Any doubt? I guess no. Let's move to the next part. This is the most interesting one. Okay, guys. But I would like to discuss one example, and it's a very good one that is for conditional probability. Okay. How we use this conditional probability in algorithms, right? It will be more related to the Bayes theorem, but I want to give you a hint, right? So in machine learning and statistics, right, conditional probability is fundamental in some algorithms, right? So what are those algorithms, right? You must have heard about naive Bayes classifier, right? So we use a lot. I mean, there are multiple applications of naive Bayes classifier. One of them, the most important one, in general we use is the spam detection, right? And again, sentiment analysis as well. Nowadays, we have a lot of good algorithms as well, but generally, like when the classical algorithm, machine learning was there, we used to use Bayes classifier. And it's based on the conditional concept of conditional probability and the Bayes theorem. We'll be discussing about Bayes theorem in detail. I just wanted to give you some idea about what is the conditional probability and when we, like where we use it. Okay. So one of the important application of the conditional probability is in hidden Markov models as well, right? Speech recognition, right? And we use it in the probabilistic graphical models as well, the Bayesian networks, right? And I want to give you a spam email classification example, right? So let's say, I mean, it's a very good thing. Like, so let's talk about the two events, right? So the event A is a, okay, event A is represent the email being spam, right? Just take a quick guess. I'm not writing it right. I don't have a slide for that. Okay. And B, the event B is what event B is trying to say, that certain word appearing in that email. Okay. So here what we try to detect, right? If that word is there, okay. So that email, okay. First of all, what is the probability of being a spam, right? I'm talking about that email, right? So that will be your first event. Okay, P of A. Now the second event is, what is the probability of being a spam email if that word is there, right? So what we try to say, calculate if that word is occurring in some emails, what is the probability of, like, what is the probability of that email being in spam? Okay, so this is one of the easiest example, right? We will take some examples at the end as well. Okay, if you have any doubt, please stop me. Okay, I'm assuming you don't have any doubt. Cool. Okay, let's move to the next section then, the Bayes theorem. Okay, yeah. So Bayes theorem is a formula that allows us to update the probabilities based on the new evidence, right? So it is widely used in medical testing, spam filtering, machine learning, and AI. Okay, so it's a very similar formula that we were using in the conditional probability. Okay, so it's nothing but, so let's say here what we are saying, probability of A given, right, B has already occurred, same thing, right? So what is the difference, right? We will be talking about that as well. Okay, so I want to ask again, if you have any doubt in the conditional probability, you can stop me now. Otherwise, we'll go ahead. Please write yes or no in the chat so that I can go ahead confidently to the next section. Okay, thank you, Justin. Okay, so let's discuss about all these terms that we have in this formula. Okay, so first is the thing that we are trying to get, the probability of A occurring given B has occurred, right? So this is nothing. We call this as a posterior probability. Okay. So now what is the posterior probability? Okay. So if the name is only fancy, it is the probability of event A occurring given that event B has already occurred. Right. So this is the updated probability, right? After considering the new evidence. So what is the new evidence here? And new evidence is B. So let's give you a very easy hint. Okay, so let's say I want to calculate the probability of event A. Okay, and I was trying to calculate it using the sample space and the total number of possible outcomes. But if I tell you, right, some event has already occurred and it's a dependent event, right? So now you have new evidence, right? So you can update the probability of A. You will get the more concrete answer, right? So that's why we use the Bayes theorem, right? So even the definition is telling you it allows us to update the probability based on the new evidence. Okay. So even if you see in the formula, we have three things, right? So we have probability of A because, as I mentioned, we were trying to calculate the probability of A, right? We have the probability of B as well because, as I said, some event has already occurred, right? But what is the likelihood of that, right? Okay, so let's talk everything in detail. Okay, now we have another term in the series, that is of B, probability of B given A is true. Okay. So this we call it is as likelihood, right? So again, it's a terminology only. So what we are trying to do here, what is P B by A or P B by A is a probability of event B occurring given that event A is true. Okay. So again, interpretation, this is the conditional probability of observing B when A is already known to be true. Okay. So here we'll be using the conditional probability application, right? This is like another application of conditional probability. We'll be using that concept here. Okay. Any doubt? So that's why I was asking again and again, if you have any doubt in the conditional probability, please let me know. Okay. So basically what it tells us how likely the evidence B is assuming A is true. Okay. The good example is we can take the spam filtering example again. So let's say the event A is an email is spam, right? And what is event B here in this case? The email contains the word lottery. So in this case, I'm saying A is already true. Okay, A is an spam, email is a spam. Okay. So again, we have some probability for that. Now, what is the probability that a spam email contains the word lottery? That we are trying to calculate that. Okay, got it? Okay. So let me give an example as well. So let's say if 80% of the spam emails contains the word lottery. So what will be the probability of probability that an email spam email contains the word lottery? And it will be 0.8%, 0.8, 80%. Right? Understood? Any doubt? It's a difficult thing, I know. That's why I'm asking again and again. If you have any doubt, please stop me. Okay, no one is having any doubt. Cool. Yeah. So let's talk about the third thing in the formula, that is P of A, the prior probability, right? Before evidence is considered, right? So prior probability is nothing but, so as I mentioned, right, we are trying to update the probability here based on the new evidence, right? So what is the prior probability? The probability of A when that evidence was not there, right? We were not aware about the B. We don't know anything about the B, right? The other event that we are considering here, right? So that is the probability of event A. Okay. So what is P of B here? P of B is the total probability or the marginal probability that we call, right? It's another term of that. Okay. So it is the overall probability of event B happening regardless of whether A is true or false. Okay, got it? So now there are three things in total, right? First is the probability of B occurring given A is true. Okay, in that case, we are considering that A is true or A has already happened. Okay, next thing is P of A prior probability when evidence P or the we don't have we didn't have any information about the event B, right? It's just pure probability of A, right? And P of B, the total probability of B, okay, regardless of whether the other event is true or false. Any doubt? This is formula. The understanding all these terms are very important. Otherwise, you'll not be able to impute all those values in the formula. That's why I'm requesting you again and again. If you have any doubt, please stop me. Okay, let's take a break of 2 minutes. I'll have some water and come back. Meanwhile, if you have any doubt, please write it in chat. Okay. Okay, anyone is having any doubt, please let me know. Otherwise, we'll move ahead. Okay, I guess no doubt. Yeah, so let's move. Okay, so yeah, so let's take example here, right? We'll try to solve some examples as well after this slide, right? So, so the example is a new virus affects 2% of the population, right? A diagnostic test is 90% accurate for infected people. That is a true positive, right? But has a 5% false positive rate as well. Okay. Incorrect false positive rates incorrectly detects diseases in healthy people. Right. You'll be discussing a lot about false positive and true positive when you will be like attending the machine learning classes, right? So if a random person tests positive, what is the probability they actually have the disease, right? I would like all of you to take the screenshot of this example, or you can watch it in the recording, right? And try to solve it based on the examples that you'll be solving in the next slides, right? Or let's solve it. So what do you want? You want to solve it in this class, or you would like to try it? If you're not saying yes, then I'll solve it in this class only. Okay. I think you want me to solve this. Yeah. So here, but it's a difficult example. Yeah, thank you, Justin. Okay. So using the law of total probability, right? You know what is the total probability? Anyone would like to take any guess? Anyone? We have discussed about it. Okay. Otherwise, I just use the formula and go ahead. Okay. So I guess okay, cool. So I'll just repeat it, and I think we have not discussed in the detail, but it's the same thing when we were talking about the mutually exclusive events, right? So when we were saying right, A union B, right? That's similar kind of thing. So the law of total probability states that if an event B can occur under multiple mutually exclusive conditions, so those multiple events are A1, A2, A3, so on, right? Could be. So we are talking about an particular event A, but A1, so there could be multiple mutually exclusive conditions, right? With that, this event B can occur, right? So if we want to calculate the probability of that, right? So how we will calculate that? So let's say the probability T that we want to calculate, right? So that will be P of T, pipe B, oh sorry, pipe D here. In this case, it is D, right? And multiplied by the probability of that event, right? That is P of D in this case, plus the probability. Now the second option could be that disease is not happening. That's another mutually exclusive category, right? Because these two events, what was the mutually exclusive events? Anyone would like to repeat here? Anyone wanna give me the example? What are the mutually exclusive events? See, I told you like all when we were discussing all those events, right? These things are very important. Okay. Anyone want to guess? Any guess? Okay. The events that cannot happen at the same time, right? It'll be great here if you guys are little bit responsive, right? Whenever I'm asking, if you are aware, then answer it, right? If you don't know, right? If you are confused, you can ask me again. I'll repeat it, right? Let's try to keep this discussion interactive, right? We're trying to solve something. Okay. So how to calculate the total probability, right? Probability of a positive test here given the other mutually exclusive conditions, right? So we'll be using the law of total probability, right? How we calculate the law of total probability? We'll calculate P of event given that another event D has already occurred. In this case, the first event was T and the event that has occurred is D, right? Multiply by the probability of that event. Similarly, the other events as well, right? So in this case, we already have the probability, right? Probability of positive test, right, is 9.9 in this case. Okay, so PT is PT by yeah. So here diagnostic test is a diagnostic test is 90% accurate for infected people, right? So true positive, right? So that is zero point 0.9 in this case. Okay. P of D is 2% of the population is new affected population, right? Okay, that is 0.02. Okay. Now the another thing is P of T, right? And when so what is this negation D? Can anyone tell me the complement? Do you guys remember the complement of D? Okay, I really wanna hear that. If you can tell me. Okay, it's okay. Yeah. So in this case, the false positive rate that they have given us, it is 0.05, the 5%. So PT by negation of D is 0.05 and P negation of D, right? So now in this case, they have not given it directly. Okay. So they have just mentioned 2% of the population. Okay. So what is the rest of the population? 0.98, right? If you just minus 1 minus 0.02, you can calculate P negation D. You guys with me? Right? So we'll get the total probability P of T here in this case by putting all those values here. So that will be 0.067. So the probability that any person test positive is 0.067. Okay. Now apply the Bayes theorem. We know PT by D, right? We know PD, we know PT now. We have just calculated, right? So that was the only missing link that was not there at the given form, given problem statement. So right, that's why we had to calculate it. Now let's impute all those values. PT by D, it's already there, right? When you know the true positive rate. Okay. A diagnostic test is 90% accurate for infected people. So they have mentioned already infected people, right? Okay, so T here T is representing the test. Okay. So the final answer is after imputing all those values is 0.2687. If you have any doubt, please stop me. Right. And I would like you to, try solve this example at your home as well. Try to, imagine it. Okay. Or you can, open some examples on internet randomly. And if you have any doubt, bring back them in the session. We will solve it. Okay. So in this case, the final probability is right 26.8%, 87%. Right? Percentage, if you represent probability in percentage, you will multiply it by 100. Okay. I guess this you all know, right? So if we try to interpret the answer, right, the test gives many false positives. So not everyone who tests positive is truly infected, right? Based on this probability, we can say that, right? So the final what are the final answers saying here, right? What we were actually trying to detect, what is the probability they actually have the diseases, right? So the question was, if a random person tests positive, what is the probability they actually have the disease, right? So that probability is 26.87%, even if the test is saying that result is positive. Okay. How it is happening? Based on the evidence that we have, right? What is the evidence here? The evidence is the true positive rate, the false positive rate, and the number of affected population. Okay. We have all these things, correct? Any doubt? Okay. I guess one is having any doubt. Okay. So what are the real world application of the Bayes theorem, right? So in medical testing, right, especially like you all are aware, right, we were like people were doing a lot of COVID-19 testing, right? So it's very important to test all these scenarios, right? We'll be, solving a lot of other things as well in the inferential statistics class, right? Basically, you'll be trying to prove some hypothesis there, right? But all these kind of tests, probability tests are also helpful, right? Used in COVID-19, cancer screening, genetic testing, all these, a lot Bayes theorem have applications everywhere, right? Even spam email filtering, we talked about it, right? We have taken few examples. Machine learning and AI, right? Nice-based classifier is a popular machine learning algorithm, right? Mainly used for sentiment analysis recommendation system. and fraud detection, right? Legal systems and forensics, right? So a lot of real world applications are there, right? So I guess we have understood, right? If you have any doubt, I can discuss all the other examples as well. Otherwise, we'll move to the next section. That is the probability theory part 2. Okay, I'll just take 2 minutes. I'll take a break of 1 minute. I want all of you to say yes or no. If you have any doubt, let's discuss that. Any doubt, anyone? Last call. We will move ahead otherwise. Okay, great. No doubt. Let's move ahead then. Okay, yeah. Let me open the new PPT. Okay, so there are some problems with my PowerPoint with this PPT, so I'll be using it in Google Slides. Okay, so the next topic that we'll be discussing today is the probability theory part 2, but here in this case, we'll be talking about the probability distributions. Okay, and it's going to be the last part of our probability theory. So from the next class, we'll be discussing the inferential statistics, right? But for that, the most important thing is the probability distributions. Okay. So I'm asking again, if anyone is having any doubt in the old section, let me know. We can discuss that again. We can solve few more examples. Okay. If you're not having any doubt, we can. Okay. So what is a probability distribution? Okay. So a probability distribution describes how the values of a random variable are distributed. Okay. Sorry, I cannot use the pen here. I will display for you. Yeah. Okay. So yeah, what is a probability distribution? A probability distribution describes how the values of a random variable are distributed. Okay. It shows the likelihood of each possible outcome in an experiment. Okay. Any doubt in the definition? It's pretty straightforward, right? What it does, it describes how the value of a random variable are distributed, right? So on a plane, on a graph, if you see, it will show you, okay, what is the range of that random variable, right? How it can move, okay? So now, like we have two types. In general, we have two types of probability distribution, right? One is the discrete probability distribution, okay? Mm. Okay, one is the discrete probability distribution. So this we use for the countable outcome. Example, number of heads in the coin flips. So you remember we solved one example, right? The trials one, right? Where I mentioned that I have tossed the coin 100 times and we got heads for 48 times only. Okay. So for that kind of thing, we used the discrete probability distribution, right? So that is used for the countable outcomes. Okay. So the next distribution is the continuous probability out distribution, right? So this we use for the uncountable or the infinite outcomes, right? Okay, like height of the students, right? We don't know how many students are there in the world, right? Okay, so that kind of things are there. Okay, so let's discuss it in brief, right? What is a discrete distribution? So definition is probabilities assigned to a individual values. Okay, in case of distribution. So example is number of calls received per hour. Okay, second is we talked about continuous distribution, right? That is for the uncountable, right? Probability assigned to the range of values, right? Height of the students, right? Because it's not countable, correct? Okay, now let's move to the next slide. Okay, yeah. But before discussing binomial distribution and the Poisson distribution, I would like to discuss the normal distribution first. And this is one of the most important and widely used distribution, right? You'll be hearing a lot about normal distribution in a machine learning class, in all the algorithms, right? There are a lot of assumptions around it. Okay. So that's why I want to give more time to this particular distribution first. Okay. So your normal distribution is, or generally known as the Gaussian distribution as well, right? So it's a continuous probability distribution that is bell-shaped in nature, right? So what is the bell shape? It'll look like this. My drawing is pretty bad. Okay, please bear with me. Okay, so it will something look like this. Okay, so it's kind of a bell, right? So your normal distribution is a continuous probability distribution that is bell-shaped. Okay, it naturally, it basically conveys the natural phenomena, right? Let's say the heights, test scores, IQ scores, right? So that all follows these kind of distribution. Okay, now let's talk about the probability density function. Okay, so this is a formula that we widely use. Okay, so here we have two things. Okay, in this formula, right? X is our event, okay, the value. Mu we all know that is mean, the center of distribution. Sigma, what is sigma? Can anyone want to tell me? Now it's kind of your revision, right? I'll be glad if can anyone tell me about the standard deviation. What is a standard deviation? Right? The answer lies in the slide only. Okay. Okay, just tell me how we calculate the standard deviation. One simple formula. Anyone would like to take any guess? Okay. I'm assuming no one knows. Okay. So please go ahead and listen all the recorded videos. I'm not gonna repeat this time. Okay. So let's discuss the probability density function in detail. Okay. So the probability density function of normal distribution is given by this function f of x equal to 1 divided by the sigma. Sigma is nothing but the standard deviation multiplied by the square root of 2 times pi, okay, into e raised to the power minus x minus mu square divided by the 2 sigma square. Okay, x is your value of the random variable, mu is the mean, sigma is the standard deviation in this case, that is nothing but the spread. E is your Euler's number, all of you know. Okay, so interpretation, right? What is this? So this function gives the likelihood of a value occurring. Okay, so larger the sigma, the curve is wider. We know what we are talking about here. Sigma basically represent your spread. Okay, this is sigma, right? We talking about the spread, right? You remember that we had curves like this, like this, right? So if sigma is wider, your distribution will be more spread out. If your sigma is smaller, your distribution will be having a curve like this. Okay, I guess you got the idea, right? It was a quick recap, but I want all of you to read that if you are not aware. Okay, so now, like we talked about this, right? Sigma. Now, what is the relationship, right? When, if you remember, right, when we were talking about the z-score, right, we used to calculate something using z-score, right? When, like, how far is the value? How many standard deviation uh, far that value is, right? So there's an empirical rule, right? So this is that empirical rule. Okay. Yeah, so this is so we have a rule 68, 95, 99.7 rule. So we call it as empirical rule. Okay. So your mean plus one standard deviation away, plus minus, right? Let me draw one graph for you guys. Okay. So this is the graph, let's say. Okay. And here it is your mean. Okay. So plus minus one standard deviation away. Okay, your 60% of your data lies. Okay, and plus minus 2 standard deviation away, right? 95% of your data lies. So that's why if you remember, we were calculating outliers, right? So it was in this segment, right? The potential outliers. Okay, after the 2 standard deviation. If you remember, like we used the term, right? Greater than 2, greater than 3, right? When we said greater than 3, right? If z score is greater than 3, then definitely it is an outlier because, right? It is what it is. It is 3 standard deviation away. That is where your 99.7% data will lie. Okay. So your remaining data will be somewhere here and here in this corner. Okay. Any doubt? Okay. So let's take one example. If height of a student follows a normal distribution with mean mu is 170 centimeter and sigma is 10 centimeter. Okay. So can you calculate the height of 68% students? Right? We'll just simply put this because we know, right? 60% of the student, 68% of the student will be in this category, right? Mu plus minus 1 standard deviation, right? So 170 plus 10 will be 180 and 170 minus 10 will be 160. So 60% of the students will be having height between 160 centimeter and 180 centimeter. Okay. Similarly, we can calculate the 95% of the students height for the 95% of the students range, right? They'll be between 150 centimeter and even 90 centimeter, right? And again, if I ask you to calculate for the 99.7%, right? So you can tell me that as well, that the height of the student will be in the range of 140 to 200 centimeter, right? With this limited information only, you are able to tell me what is the height range. Okay. Remember this, this has a lot of application in the machine learning space. When we'll be discussing about the machine learning algorithm, we'll be using these principles. Okay. Now let's talk about the how the normal distribution graph looks like. Okay, I'm gonna show you that in the notebook as well, right? And how to draw that. We will discuss that. Okay. So first of all, as we discussed, normal distribution is a continuous graph. Okay, because here we are talking about the continuous values. Meaning, what are the continuous values? Anyone wanna take a random guess? I told you, right? When we were discussing about the continuous and finite possibilities, right? Uncountable thing, right? So it'll be representing by only represented by a range only, right? Meaning it can take any real value, right? Okay. So it has a bell-shaped curve we already discussed, which is symmetric around the mean. Okay. So your bell-shaped curve that we discussed will be symmetric around the mean. So this will not look like a symmetric around the mean, but this will be symmetric around the mean, right? So they are your mean mu. Okay. The probability decreases as you move further away from the mean. Okay, if you go down, down, down here, further away from the mean, the probability will decrease. Okay, the spread of the curve is determined by the standard deviation. You already discussed, right? We discussed about the empirical formula, the shape of the normal distribution, because it is determined by the spread only, right? Sigma, right? So 60% of the data lies within the one standard deviation. 95% of the data lie within the two standard deviation and approximately 97.7% of the data lie within the three standard deviation. Okay. Yeah. So what are the properties of the normal distribution? Few we have already discussed. It is a bell-shaped curve, right? And this we discussed briefly, like when we were discussing about the mean, median, and mode. So in this case, if you have a normal distribution, this is the property of a normal distribution. All three things will be equal and it will be perfectly centered, right? Because as we mentioned, it is symmetric around the mean, right? So it is defined by the two parameters only, mu, that is mean, and the standard deviation. Okay. So the total area under the curve is 100% 100% probability. Okay, that basically represents the 100% probability. The complete, because it's a probability distribution only, right? Okay, so this the total area below this curve is 100% probability. Okay, it follows the empirical rule 68, 95, 99.7%. Okay, This we have already discussed. Okay, now let me show you this in a notebook. Okay, I'm gonna share my other screen. Okay, you can see that. Let me open that. Okay, can you see this? Anyone? Everyone? Okay, first let's see the normal one. Okay, I would like anyone to confirm this. Can you see? Justin, Ashish, Raini, can you guys see my notebook? Okay, thank you, Justin. Okay, so let's visualize normal distribution with mu equal to 170 centimeter. That was the average height. You remember the form? I mean the example that we were discussing, right? The average height of the students, right? And I mentioned that the spread, the standard deviation is 10 centimeter. Okay, so let's put all those things in the. Again, we'll be using the SciPy library only. From the SciPy.stats, we have imported the norm. That is not particularly normal distribution. Okay. So first we have a mu, that is nothing but the mean is 170 centimeter. We have sigma, standard deviation is 10. Okay. So now let's create a range of values, right? So we have a formula like in the NumPy library. Let's create a range of values. NP dot length space. So it's mu by 3 into sigma plus mu by 3 into sigma. And, so 100 values, like we are looking for this number range of values, right? So you remember why are we doing it? Can anyone tell me why are we taking this much space only? Right? It's because of the empirical rule that we just discussed, right? Your 99.7% values will lie between plus minus three times of your standard deviation, mu plus minus three times of your standard deviation, right? So X will become your range of values and norm.pdf, right? So we'll just pass this x, that is the range of values, right? These are the values here. They'll be between 140 to 200, right? Because we got it from this x, right? And then uh, we are passing the values like mu and sigma, the mean of that probability distribution, and the sigma here is this standard deviation. Okay. So now let's plot that. Okay. We already have x here, that is the range of values, right? And y is the probability of that. Okay. So here, if you see, this will look like this because it's a normal distribution, right? It is symmetrical around the mean, 170, right? And if you calculate the spread, right, using the sig mu, it'll be like 68% of the data will come in the plus minus one mu plus minus one standard deviation. Okay. So here x-axis represent value height in centimeter because we have created the range using the mu and the sigma that we had, right? Y-axis represents the probability density, not exact probability. Okay. Peak at mu equal to 170, as I said, it'll be symmetric around the mean, right? The most common height is 170 centimeter, right? Because this is our mode as well. You remember when we were discussing about the properties of a normal distribution? Mean, median, mode, both are on the same axis and all three are equal, right? So values close to mu have higher probability because values between 160 to 180 centimeters common, right? Empirical rule, remember? What are the extreme values here? Extreme values in this case is 140 centimeter to 200 centimeter because these values are three standard deviation away from the mean. Okay. So the conclusion, normal distribution is widely used in real world data modeling, right? Including height, IQ score, test scores, and stock prices, right? So yeah, I want to give you a picture, the similar example here I'm taking, right? I want to give you the picture of all this. Okay. So here, this curve is your normal distribution. Okay. The black dotted line is representing your mu. If you see this properly, your curve is symmetric around the mean, right? It's the mirror image of each other, right? Can you guys imagine? Okay, I hope all of you can imagine, right? So now the red dotted line are basically telling you the one standard deviation, right? Right. So mu plus one standard deviation away, mu minus one standard deviation away. The values are 160 and 180, right? So here in this case, 60%, 68% of your data will lie. Okay, correct? And if you move away to the two standard deviation, right? So in this case, your 95% data will look like. Okay. Now you guys can imagine, right? And as you as you remember, right, when we discussed, right, anything away from the three standard deviation, that is nothing but a green line here, sorry, will be an outlier in that case. Okay. So now you guys understood, right, how spread is helping us to determine the distribution, right? The spread shows how far the data points deviate from the mean, right? Most data is within the two standard deviation. That is the 95% data. Okay. Any doubt here? Okay, I'm assuming in the interest of time, I'm assuming you don't have any doubt, but please stop me and write it in chat if you have any doubt. Okay. Now let's, can you guys see my PPT? I'm moving to the next slide, right? So let's try to solve a quick example that is again related to height of students. Okay, so we have height of students. When I'm saying height of students follows a normal distribution, right? With a mean of 170 centimeter and standard deviation 10 centimeter, right? So now I want you to tell me what is the probability that a randomly selected student is taller than 180 centimeter. Okay. So first of all, we will calculate the z-score for that. And you know the formula for z-score, right? Z-score is nothing x minus mu divided by sigma, right? So let's impute the values. It is 180 minus 170. 170 we know the mean, right? And sigma in this case is 10. The final answer will be 1. Okay. So using a z table, right? We have a z table, right? So if you read study, you will be having a z table. With the help of z table, you can just see what is the probability with for z greater than 1, right? So that will be 0.1587. Okay. So here, what it said, okay, what the question was, what is the probability that a randomly selected student is taller than 180 centimeter? Okay. So in that case, we'll be checking the anything greater than z greater than 1 will be my answer. Okay. So the final answer will be 15.87% of the students are taller than 180 centimeter. Okay. Can anyone tell me what z score tells us? Anyone? I just told you, right? Z score tells us how far is that value. How many standard deviation away is that value? Okay. Got it? Cool. Let's move to the next thing. So yeah, we'll be comparing them later. Let's start with the initial of the PPT. Okay. Yeah. So let's talk about the binomial. We talked about the probability distributions initially, right? We talked about two types of distribution, discrete and continuous distribution, right? So let's talk about the binomial distribution now. Okay. So I took the extra time for normal distribution because it's the widely used distribution, and we'll be discussing a lot about it, right? In our machine learning classes. Okay. So what is a binomial distribution? A binomial distribution models the number of successes in a fixed number of independent trials. Okay. Where each trial has two outcomes. Okay. Either success or failure. Right. And you know, right, when we discuss the complement of the probability, right? So let's say probability of event A is x, so what will be the probability of event a dash, right, will be 1 minus x, right? So let's say a is your success here, so what will be the probability of failure will be 1 minus x. Okay, so how we represent it, right? Formula of binomial probability, right? So p of x equal to k represented by nk, p of k 1 minus p n minus k. We'll be solving this. Nk is the combination formula. I'm assuming you guys knows about it. Okay. So here where let's see what are all those terms. N is the number of trials right? So as I mentioned, right, in the definition itself, binomial distribution models the number of successes in a fixed number of independent trials, right? K is the number of successes. You remember we discussed about one example, right, where I have tossed a coin 100 times, right? And we got heads 48 times. Okay. So similarly, here the number of trials are 100 and number of successes are 48 because I got head only 48 times, right? P, what is P? Probability of success in one trial. Okay. And NK is nothing but a combinations formula. Okay. In N case, NK is represented by that n factorial divided by k factorial minus n minus k factorial. Okay. Okay, now let's talk about how this binomial distribution graph looks like. We will see this graph in the notebook as well. Okay, so characteristic of a binomial graph. Okay, so binomial distribution is discrete in nature, right? Meaning it will only takes value integer value 0, 1, 2, and right. So it shows probability for a fixed number of trials, as I just mentioned in the definition itself, right? Where each trial is independent, and you know what is an independent trial. I don't have to repeat it. That's why I was keep on mentioning, right? Ask me if you have any doubt. What is the independent trial event? What is a dependent event or a trial, right? So all these things are helpful in understanding all these concepts. Okay. Now the graph looks like a histogram, the bar chart, because of the discrete events, right? It cannot be a perfectly smooth curve, right? Because here we are talking about in discrete events, right? It will be like this, right? We will be having histogram. Right? It cannot be like this. Okay, it's not a continuous distribution, correct? So the graph looks like a histogram bar chart with peaks around the expected number of successes. Okay, as n increases, the number of tile increases, the graph becomes smoother and begins to resemble the normal distribution, right? So generally we say as n tends to infinity, right, your binomial distribution will start looking like a normal distribution. Okay, see shapes of the binomial distribution, right? The shape of a binomial distribution depends on the probability of success, right? This is very important. Okay, and the number of trials. Okay, if p is equal to zero point 0.5, the probability of success, right, that we discussed. Okay, the distribution is symmetrical. Okay, if p, the probability of success is less than 0.5 or greater than 0.5, the distribution will be skewed, right? And you guys remember, right, how to identify a right skewed or left skewed distribution, right? We discussed about it, correct? If you're not aware, please go through the old recordings. Okay. And as I mentioned, as n increases, the shape approaches to a normal distribution, right? We will discuss about it in the center limit theorem as well, right? This is one of the interesting algorithm, right, or a theorem, and commonly asked in all the interviews, in all the data science interviews, right? I mean, it's very rare if people are not asking about the central limit theorem in a data science interview. Okay, let's try to solve a coin toss experiment using the formula that we have, right? So let's let's toss a coin 10 times. Okay, so here we are tossing a coin 10 times. So what is the coin here? So what is n here? N is the 10 total number of trials, right? Find the probability of getting exactly 6 heads, right? So the number of successes is 6 for us. Okay, so we have all the values for us, right? N is equal to 10, k equal to 6, and what is the probability of getting a head is 0.5, right? Because you remember 1 by 2, 1 is the favorable outcome and 2 is the total number of outcomes from that event, right? Okay, let's impute all those values. Nk, right, the combination formula, 10, 6 will come here because n is 10, 6 is the k is 6, 0.5 into power 6. You remember this formula, right? P of k, P of k is coming here, and then negation of p power n minus k. Okay, that is nothing but 4. So let's try to solve it. We'll be ending up with the values is 0.205. So the final answer is the probability of getting exactly 6 head is 20.5%. Okay, any doubt? I'm assuming this no. Okay. Uh, so please take the screenshot of this example and try to solve this at home. Okay. If you have any doubt, ask me. Okay. Now let's talk about the next distribution and the last distribution that we have. Okay, for the session. This is the Poisson distribution. Okay. So a Poisson distributions model the probability of a given number of events occurring in a fixed interval or time space. Okay. Assuming events occur independently and average rate. Okay. Lambda is known as constant at an average rate. Okay. So formula for Poisson probability is P of x equal to k is again the number of events occurring, right? E to the power minus lambda. Lambda is the average number of events per interval. Okay. Lambda to the lambda power k and divided by the k factorial. Okay. So let's talk about all the terminologies here, right? Lambda is average number of events per interval. K is the number of events occurring, and E, Euler's number. Okay. So how is the graph looks like? The characteristics of the Poisson distribution graph. Again, it's a discrete distribution. Poisson distribution is discrete, meaning it takes only integer values like the binomial distribution. It represents the probability of a given number of events occurring in a fixed interval of time or space. Okay. The graph has a right skewed shape for small values of lambda, but becomes more symmetric as the lambda increases. Okay, it's just like the binomial distribution, as you were saying, when the number of trial increases, right, your distribution will move towards the normal distribution. Same thing is happening here, right? Let's talk about the shape of the distribution. If lambda is small, right, the graph is highly right skewed, asymmetrical, right? If lambda is large, right, the graph becomes more symmetric, almost resembling a normal distribution. Okay, let's try to solve an example, right? So you will get the idea, right? How, like all the terminologies that I was discussing about, right? A call center receives 5 calls per hour on average, right? So here, if we talk about lambda, right? What we discussed, right? What was lambda here, right? Lambda is the average number of events per interval, right? So here, the interval length is 1 hour, okay? And how many events are happening in that interval? Is 5. Okay. So what is the probability that exactly 3 calls arrive in the next hour? Okay. So here, what is the K? K is 3. And what was the K that we discussed? Is the number of events occurring. Okay. So we know lambda equal to 5 and K equal to 3. Let's put all those values. We want to know P of 3, right? In this case, X equal to 3, right? So we'll impute all those values here in the formula and we'll end up with this. The probability of receiving exactly 3 calls in 1 hour is 14.04%. Okay. So using these distributions, right, we can calculate the probability for a particular event. Okay. Cool. Now let me share my screen again, the notebook again. I want to show you these distribution in the notebook. Okay, let me share my screen. I hope it is visible to all of you. Okay. So this is how your binomial distribution looks like. In this case, if n is 10 and p equal to 0.5, the probability of success. Okay. So again, if you see here, we are using the SciPy library only, scipy.strits. We have imported all the distributions from here, the formula, the functions, binomial distribution function, Poisson distribution function, and a normal distribution function, and we have already discussed, right? So we are imputing the values here, right? That was discussed in the slides, right? So in case of Poisson distribution, we have lambda, that is 5 calls per hour, right? So in the Poisson.pmf, right, we will impute x. We are just making a range here, right? Np.range 0 to 15, right? We are just taking a random range, right? That's the number of calls, right? So we have this x and the lambda, we know the rate, right? So this is how it looks like. Okay. And if we talk about the binomial distribution, and it is a discrete, that's why it's coming as a bar graph, correct? Similarly, if we talk about the binomial distribution, we know the total number of trials is 10 in this case, and the probability of the success is 0.5. We'll impute these values and we'll impute the range as well. For that, we want to calculate calculate these all these probabilities, right? This is how it will look like. Okay. Same thing, we have done it separately. Okay. This is how your graph will look like. Okay. So interpretation of graph for binomial distribution will be here x-axis representing the number of success. Okay. Y-axis representing the probability of each value of x, right? So let's say if we're talking about 6, right? What is the probability of 6 calls, right? Or 6 successes, right? So that will be this much. By seeing graph, you want to see that it will be 20%. Okay. Understood? Okay. The graph is symmetrical around the expected value of x n equal to 5, almost symmetrical, right? This means we are most likely to get 5 heads in 10 flips. Okay. But we could also get 4 or 6 heads with a high probability, right? If you have any doubt, let me know. Okay. Now let's visualize the Poisson distribution. The same example that we took, lambda equal to 5, average of 5 customers arrive per minute, or 5 calls arrive per minute, right? So X is basically representing the number of occurrences in a fixed time, right? 0 to 15, we are just taking an example, right? And Y is your Poisson distribution, probability mass function, we are using a function, Poisson.pmf. X, we are passing the range here, and lambda we are passing, right? That is 5 for us. Okay, so based on the graph also you can see the probability, right? What we were trying to find, like for 3, right? It is between 2 and 4. It was about around 15% when we calculated, right? If you remember, right? So when we calculated, it was around 14.04% when we calculated using the formula. And similarly, we can depict it from the graph as well. Right? It is below 0.15, right? It's around 14% only. Okay. So peak occurs around lambda equal to 5, right? Here. And meaning 5 events per interval is the most likely scenario. Okay. Any doubt? So conclusion is the Poisson distribution graph helps us, model random events occurring over time and space, such as examples are customer arrivals, consult volume, website hits, right? The real world examples can be if you want to know the number of petrol pumps required, right, on your petrol pump. Let's say you have a fuel station, right? Now, how many fuel pumps you want to keep there, right? So that you can handle the maximum customers, and right, and your crowd should not wait, right? So these kind of problems we try to solve using this type of distribution, Poisson distribution. Okay. Any doubt so far? Let me know if you have any doubt. Okay. So any yes, no doubt. Okay, cool. So I guess no one is having any doubt. If you have, sure. Let's continue the class in next step. I'm done with the probability anyhow. Okay. So thank you everyone. Thank you for attending the session. Okay. We'll be starting the inferential statistics in the next class. If you have any doubt in the probability, please let me know. We can discuss that again. Okay. Thank you everyone. Thank you for joining. Have a nice evening.